Welcome. In this talk I'm going to go through and start deriving the ideal MHD equations and show essentially from physical arguments where it comes from. I won't do the full derivation, so in later lectures I'll go through and try and derive them from first principles, from the kinetic equations. In this talk I just want to start from the Euler Equations, which are the equations for a fluid, which we've derived in several different ways, just for neutral fluids, so gases and liquids, and then introduce the electromagnetic forces which occur when you have a conducting fluid. So now we're going to allow the plasma, or treat plasmas as a gas or a fluid which conducts electricity. And so we couple the fluid equations to electromagnetic effects, so to Maxwell's equations. I'm going to summarize then the main assumptions that the model makes, and then give very briefly some applications which we'll expand on in later talks. So first, the Euler equations. So for neutral fluids, the Euler equations, and these can be derived just from conservation of mass, momentum, and energy. And the equations we get are for the mass density rho. So this is like kilograms per cubic meter. We get d rho by dt. And u is the flow velocity of the fluid, so just meters per second. So u dot grad rho, and then here we have a minus rho divergence of u. So here u is the flow velocity. U. And this the equation for u comes from the conservation of momentum. So we have du by dt plus u dot grad u. And then here we have essentially the forces. So if we write here the mass density, this is the momentum per volume. So this is like kilograms per cubic meter, this is meters per second, and this is essentially the acceleration. And so here on the right hand side we have forces per volume. So we have the pressure gradient, and then we can have other external forces. And these are in basically newtons per cubic meter of the units of this. So there's force per volume. And examples we've seen previously are, for example, rho g, where we have gravity. Or we might have viscosity. It's like a more complicated expression, but it's just another force on the fluid. And then this talk we're going to introduce electromagnetic forces in here very shortly. So you have conservation of mass, conservation of momentum, and then this introduces a term for the pressure, and so we have a pressure equation which comes from the conservation of energy. Pressure P, and we have a dP by dt plus u dot grad P. Then here we have a gamma, ratio of specific heats, and then divergence of u, so this is the compression term. Okay, so these are for neutral fluids. We're going to apply the same model to a plasma as a fluid, and so we still have conservation of mass, momentum, and energy. So these three equations still apply. The only thing really that changes is the force, and so we have a force on a conducting fluid. So force, and this just if you have a current in a magnetic field, conducting fluid, then you have a force. So for example, if we have a simple case where you have a current I in a wire, so this is a wire, and we have a magnetic field which is perpendicular to that wire, so it's B. We have a length L. We have a force is just B times the current times the length, and this would be in newtons. Now if you have a small bit of fluid, so we have a cross section like this, we have some kind of parcel of fluid which is carrying some current down through it. So here we have a J, which is a sort of amps per meter square. So it's the current density. So each meter squared of cross section here carries this J times amps. if you have a magnetic field, this is sitting in essentially like a wire sitting in a magnetic field. So if you have a magnetic field across this fluid, then we have a force, and the force is just J cross B. And this force, this has units of amps per square meter, and then here we had an amps times a meter, and so the units of this are newtons per cubic meter. This is the force per volume, and so we can just essentially add this to the Euler equations. So we have an external force, and now our fluid is carrying a current density J, and it's in a magnetic field B, which might also be generated by the fluid itself, and so we just have this J cross B term, and so the momentum equation just becomes du by dt plus u dot grad u. So this is all the same as before, and then here we have the rho term here, so minus grad p, and then plus J cross B. That's it. That's essentially the modification. So this is ideal. This is the ideal MHD equations. The problem is then we have essentially J and we have B, and it's working out what these terms become, because now we need equations to determine what the currents are, what the magnetic fields are. There's a vector as well. So calculating J and B. So we have some unknowns in the equations, and now we need to close the set of equations again. So we need to come up with some equations. Now, one of the key assumptions of what makes this ideal MHD, rather than the more complicated models, is the Ohm's law. And so what we do is we assume the electric field is 0 in the frame of the fluid. So assume E equals 0. So when the fluid velocity equals 0, then the electric field is equal to 0. So if you move into a frame moving with the fluid, then you don't see any electric field. And this is equivalent to just saying that the resistivity of the plasma is 0. So i.e. no resistivity. Now, if you change frames in special relativity or in electromagnetism, you can transform basically electric fields into magnetic fields. And in a frame moving with the fluid, you have E equals 0. If you move into the lab frame where you have a fluid flow, what you find is that this E in the plasma frame is basically E in the lab frame plus U cross B, and this we're saying is equal to 0. So in the lab frame you have E plus U cross B is equal to 0. So in the lab frame where we're measuring the flow of the fluid, and this is the ideal MHD. Ideal MHD Ohm's law. So in extensions to ideal MHD, where you have resistivity, or we might have the Hall terms or other pressure driven electric fields, you might have other terms on the right hand side here. And so ideal MHD is unique in having 0 on this right hand side. And this has quite a lot of other important consequences that we'll look into later, which can be broken when you have things like resistivity. So this links essentially the magnetic field and the flow to electric fields. And so we have equations for electric fields and magnetic fields, and so we can start to write down how this couples to Maxwell's equations. So the first one we look at is, so we have dB by dt. So we want to know how does magnetic field evolve. Let's just curl of E. This is Faraday's law. Okay, and then we can just essentially substitute this equation we have here into here. So we end up with So this is in the lab frame. So we're going to take this E from here and substitute it into there. And so we have, this is just curl of U cross B. So the rate of change of magnetic field in the lab frame is equal to this curl of U cross B. And that's the first sort of useful expression that gives us how the magnetic field changes with magnetic field and velocity. So we now have an equation for B, which involves things that we know, so just the fluid. The other part we need to know is the current. So we need to know how's the J, how is J determined. So now we need an equation for the current J, and to do that we can use Ampere's law. So we have curl of B, and we have mu naught J, and then we have Maxwell's terms, the displacement current. So we have mu naught epsilon naught dE by dt. And so this gives us an expression for the current in terms of the magnetic field, and here above from Faraday's law we have an equation for determining the magnetic field. We have this term, it says the displacement current, and this, because this here is 1 over c squared, so mu naught epsilon is 1 over c squared, so this term actually only becomes important when you have quite high frequency waves. And so for MHD we neglect this term. So I've actually assumed that this term disappears. And this is only valid for low frequencies. So this is for low. So if you want to study how light waves or how radio waves travel through plasmas, then these equations can't be used, because then this term would be important. But for low frequency phenomena, we can neglect this term, and that essentially takes out light waves. It removes quite a fast wave from the system. Another consequence of this is that if you take the divergence of this equation, so we have so divergence of a curl is identically 0, and so this implies that divergence of J is also identically 0. And this condition is essentially quasi-neutrality. Quasi-neutrality. So this appears in several different forms depending on how you look at the assumptions. But this is consistent with a case where there's no charge build-up. So if you have divergence of J is 0, then you can't have charge accumulating in any one location. And so there's very small charge imbalances. So no net charge. So there's no net charge in the plasma. Whatever current goes in always comes out, and the current just flows around in continuous kind of loops. Okay, so together with this equation, so here we have an equation for B. This equation we have here, it's the reduced form of Ampere's law. Ampere. So Ampere's law. This equation, the induction equation from Faraday's law, gives us all the equations we need to solve this set of equations. So we now have an equation for B, we have an equation for J, and we can solve this set of equations. So we have, this is the summary of ideal MHD. So now we have equations for the full ideal MHD. So we have the usual fluid equations, so mass density, flow velocity, and pressure. And now we also have an equation for magnetic field. And so it's a closed set of 8 equations. Because we have 3 from the velocity and 3 from magnetic field. If you use the divergence of B as 0, so that removes one of the degrees of freedom, and so there's actually 7. So if divergence of B equals 0 is included. that then removes one of the degrees of freedom here. So the equations are the mass density, d rho by dt, over u dot grad rho. So this remains unchanged from Euler's equations. Then we have a du by dt, so the momentum equation. And then this is essentially the only fluid equation that's changed, so a sort of pressure term. We have now the electromagnetic forces, so J cross B. Then we have the pressure equation still, so dP by dt. Because U dot grad P is minus gamma P to U. And then we have finally the induction equation, so we have dP by dt. It's curl of U cross B. And then this essentially gives a closed set of equations. The only extra thing we need is that the current density J is just 1 over mu naught curl of B. So if we know B from this equation, we can calculate J. Okay, so this is the ideal set of ideal MHD equations. And then the main assumptions we've made. So main assumptions. So first of all, we've used the Euler equations essentially for the fluids, so that all the same assumptions as we made there apply. So we have frequent collisions. We're assuming that we have local thermodynamic equilibrium, so LTE. And so we can define a local temperature, and the mean free path is short. So this means you have short mean free paths, and so the length scales must be long compared to things like the Lama radius. So length scales must be bigger than RL, so Lama radius. Because in the perpendicular direction to the magnetic field, this is the more relevant one than the collision length, for example, because the particles are constrained to lie on to go round and round in circles. But nothing in the model knows about Lama radius scales, so we need to have length scales much longer than that. We need to have frequency and frequencies which are small. So frequencies of the oscillations that we're looking at must be smaller than the cyclotron frequency, so the frequency that the ions, for example, go around their orbits. And of course much less than the collision frequency. And we've assumed that the plasma is quasi-neutral. So quasi-neutrality. Quasi-neutral plasma. Which in general is also consistent with the low frequency assumption. So we assume that everything is very slow compared to things like typical speed of light kind of waves. And these assumptions are still valid in many different regimes. So it's used for things like large scale stability of laboratory plasmas. So if you want to look at very small scale, like turbulence fluctuations, then these things start to fail. So if you have turbulence in tokamaks, for example, or other fusion devices, they can be significant around the Lama radius scale, and so this assumption starts breaking. If you're looking in the core of the plasma, the collision frequency can become very, very low, and the collision length, the distance between collisions, can become very long. And so the hot core region of laboratory plasmas, these assumptions can start breaking down. The other place where these are used, things like solar or astrophysical applications, where you have very large systems, and even in those cases, unfortunately, these often need extra terms adding. So in all these applications, ideal MHD is a good approximation, often much better than you'd expect from these assumptions. But usually needs some additional terms adding to it to fully explain what's seen experimentally or observationally. And we'll go through in the next few talks how these terms are added, what assumptions need to be made, and how MHD can be improved.